A network exists when you have two or more devices that share data. As you saw in the previous unit, a network is composed of many different physical parts that work together to ensure your data gets to where it's needed. This transmission of data across a network is enabled by a suite of communication protocols, often referred to as TCP/IP. It's named after the two main protocols: Transmission Control Protocol, TCP, which handles the connection between two devices, and Internet Protocol, IP, which is responsible for routing information across the network. Every network on the planet shares and moves data every second of the day. This data comes in every shape and size, from a simple message to images, and even the movies that are streamed to your home. The datagram or packet. Networks exist to help make device-to-device or system-to-system communication easier. Whatever the size of data, it all needs to be broken down into tiny uniform chunks. These chunks are called datagrams, but are also more commonly known as packets. Imagine that you want to stream a movie to your device. Given the enormous size of the data involved, the streaming server can't give you the whole movie in one go. Instead, the movie is broken up into billions of packets. Each packet contains a small part of the movie, which is then sent to your device. Your device has to wait until enough packets have been received before you can start watching the movie. In the background, the server continues to send a steady stream of packets to your device just ahead of what's being displayed. If your network speed slows down, then the packets may not reach you in time. The picture you see might become distorted or blocky, and there may be gaps in the sound. IP addresses. When you want to send a letter to a friend, you'll first write it out before putting it in an envelope. Next, you'll write your friend's address on the envelope before posting it. The postal service collects the letter and, through various sorting offices, eventually delivers it. Networks operate in a similar manner. The message is contained in the packet like an envelope. Then the sender and recipient addresses are added to the packet. The primary function of the Internet Protocol, IP, is to ensure that every device on a network can be uniquely identified. Before a packet is sent across the network, it must be told the IP address of where it's going, and the IP address of where it's come from. There are presently two standards of IP address, the IPv4 and the IPv6. The details are beyond the scope of this module, but the most common type of IP address, and the one you may be familiar with, is IPv4. This is made up of 4 groups of digits separated by a dot, for example. DNS. Just like every device on a network needs a unique IP address, every public-facing website has its own IP address. You could use the IP address to visit your favorite online retail store, bank, or streaming video service. But with so many websites available, that would be difficult to remember. Instead, you type the name of the service you're looking for into your browser and it takes you to the website you want. This is all thanks to the Domain Name Service, or DNS. The DNS holds a table that has the name of the website, for instance Microsoft.com, which maps to its corresponding IP address. Your browser uses this to find the actual website in much the same way as you might use a phone book to find a telephone number. Each time your device connects to the internet, it uses a local DNS server to find the name of the website you're looking for. If the DNS can't find the site, it checks other DNS servers. If the site can't be found, or the request times out, you'll get an error message such as DNS server not responding. Routing. When the IP addresses have been added to the packet, it's ready to be transmitted across the network. If the IP address exists on your network, the packet is sent directly to the device. However, if the IP address is outside of your network, it needs to go via a router. A router is a physical device that connects one network to another. Using our letter scenario, if your friend was only a few streets away, you might decide to deliver the message by hand. Your friend is within your local network. However, if your friend is in a different city or country region, you need to post the letter and let the mail service deliver it. In this instance, the postal service is the router. It takes the message from your network, then finds the best route to get it to your friend's network for delivery. Video animation. In this short video, you'll see how everyday activities form networks, from speaking with your friends on the phone to sharing emails. Then you'll look at the way messages are broken down into packets, that can be sent across the network.
Networks exist everywhere, and they communicate with each other all of the time. They do this using TCP/IP to manage the sending and receiving of packets of data. All messages, regardless of size, need to be broken up into fixed-length chunks called packets. Here we have Kayla, who wants to send a message to Monica, who lives in a different part of the world. She composes an email using an app on her device. "Hi Monica, how are you today?" When she presses send, the message gets processed by TCP/IP. It knows who the sender is and who the recipient will be, in this case, Monica. TCP/IP accepts the message and breaks it up into packets, and then assigns the sender and recipient IP address to each one. TCP/IP then makes sure that each packet is sent via a router across the internet. Here we have a simple representation of a network stretching across the world, made up of a number of routers or nodes. In reality, there are hundreds of thousands of routers in every country. Trillions of packets zip around the network every second, but we'll slow it down to show you how routing works. Each router or node knows which of its neighbours offers the best connection. This can change on a packet-by-packet basis. Kayla's message has already been split into packets of data and is ready to send across the network. The first packet is sent by the most direct route and arrives at Monica's device. Before the next packet can be sent, the previous path goes offline. This means the next packet will have to take a different route to get to Monica's device. As the third packet is ready to send, a node in the network drops out, meaning the network packet needs to find a different route. The last packet is ready to be sent, and another node is running slowly, so a new faster route is chosen by the network. All these packets are being sent in tiny fractions of a second. All the packets have now arrived at Monica's device and are reconstructed so that she can read the whole message.